Assalamu alaikum guys, welcome back to the channel. So today's video is gonna be for A-level chemistry students, those who are appearing for their A2 chemistry exams, P4 and P5. And based on a lot of requests from many of you guys, many of you were confused on the topic of buffer solutions, which is in further aspects of equilibrium. So that's what we're gonna be focusing on today. This basically is a marathon of buffer solutions, meaning that I'm going to assume you have absolutely no idea of buffer solutions. You have zero idea about it. So just forget everything and just focus on this one stream slash recording. And then you shall be good, inshallah, for your P4 exams. Right. Now, let's start. When we talk about a buffer solution, you first need to understand what do we actually mean by a buffer solution. A buffer solution is a solution which resists the changes in pH when small amounts of acid or alkali is added to it. So a buffer solution is not anything special. It's just a simple solution right here. And in this solution, if I add a small amount of acid or if I add a small amount of an alkali, it's gonna resist the change in pH which could have been brought about by the addition of an acid or a base. So basically, it opposes any change which could have been brought about because of an acid or a base. This is the first definition you need to learn, and they're going to ask you this straight up in the exam. So the first question is define a buffer solution. So we now know the answer for it, that a buffer solution is a solution that resists changes in pH when small amounts of acid. So it's basically a choice, right? There can be questions wherein they add a small amount of acid to the buffer solution or they add a small amount of base to the buffer solution. So when small amounts of acid or base are added to the solution. Okay, now when you talk about a buffer solution, there's two types of buffers basically which is included in your syllabus and you should know about them. So the first type of a buffer solution is called an acidic buffer. So you understand it has something to do with acids, right? And the second type of a buffer solution is called a basic buffer. We're going to be focusing on this first, and then we'll come to this later. 95% of all buffer questions in your P4 exam are going to be from acidic buffer. Take this from me and trust this. Acidic buffer is going to be 95% of all your buffer solutions. The remaining 5% is basic buffer. I've rarely seen two questions from basic buffer, so you don't need to worry about this. Only worry about this. So let's start with an acidic buffer. How do we actually create the solution? As in, what is the things or what are the compounds that are present in the solution? So, whenever you talk about an acidic buffer, it has, or you could say it's a mixture of a weak acid and the salt of the weak acid. So let's first understand what a weak acid is. Now, most of you would know this. For those who don't know, a weak acid is an acid which partially ionizes when in aqueous solution. So let's take an example. If I have HCl, when I draw the dissociation of HCl, meaning when I put HCl into a solution which is water, the HCl dissociates, or you could say breakdowns into its ions. And how does it break into? It breaks into H plus and Cl minus. Notice the arrow which I used to explain this dissociation is a forward arrow. What is that telling me? It's telling me that every single HCl molecule in the solution dissociated to formed H plus and Cl minus. Meaning now there are zero HCl molecules in the solution, meaning zero molecules are undissociated. This is what we call complete ionization of an acid. If you're confused what the word ionized basically means releasing H plus ions. So HCl completely ionizes. Every single HCl forms H plus ions. Now let's say if I have ethanoic acid, CH3COOH. Ethanoic acid is a weak acid. So it's not gonna completely ionize. Not every single ethanoic acid molecule is going to dissociate into its ions. Only some of them will dissociate, and the majority of ethanoic acid molecules are gonna stay as it is. They will not dissociate even when we dissolve them in water. So you're not going to draw a forward reaction to show the dissociation. You're going to draw a backward reaction. And this is going to dissociate into the anion, the negative ion, and obviously the H plus ion. So there we have it, the weak acid being dissociated. This is the first part of an acidic buffer. Look at what the second part is. The salt of the weak acid. Meaning, how do you write the salt of a weak acid? All you have to do is replace this H with any metal. So you could say sodium metal, you could say calcium metal, you could say potassium metal. Take any random metal and put that in place of H. So let's say I take sodium. So CH3COONA. Now, you must have learned this in IGCSE that all sodium salts are water soluble. What's a sodium salt? A sodium salt is basically a salt which has sodium in it. A potassium salt is a salt which has potassium in it. All sodium salts are water soluble, meaning when I dissolve this compound, which by the way is a sodium salt, into water, every single CH3COONA, I'm gonna tell the name later, every single one of this molecule is gonna dissociate into its negative ion, which is CH3COO minus, just like we did it for the acid, and the positive ion. But now look at this. The positive ion is not going to be H plus because there is no H plus here. It's going to be Na plus. So that's the same dissociation as for the acid. Just in place of H plus, you have Na plus. Take a look at this. Only a forward reaction. Think about it. Why? It's because all of the sodium salts are water soluble. They completely dissolve and completely dissociate when in aqueous solution. So never make the mistake in the exam of drawing this as a reversible reaction, of drawing the reversible arrow. Never do that. You only draw the reversible arrow for a weak acid, and you draw the complete forward reaction for the salt of the weak acid equation. So there we have it. If someone asks you what is this? If someone asks you what is in a buffer solution, in an acidic buffer solution, so now you know we have the weak acid. So let's say we have ethanoic acid. This partially dissociates into ethanoate ions and H plus ions. And we have the salt of the weak acid, which by the way is called sodium ethanoate. Why do we call it sodium ethanoate? Because the way you name a salt of a weak acid is you first write the name of the metal, so sodium, and then you write the name of the carboxylate ion. This is carboxylate ion. Why do we call it carboxylate ion? Because where was it formed from? It was formed from a carboxylic acid. So whenever you have to name a salt of the acid, it's metal and then carboxylate, ATE at the end, not acid at the end. So it's not sodium ethanoic acid, it's sodium ethanoate, potassium ethanoate, calcium ethanoate. So only a forward arrow, and you get CH3COO minus, which is ethanoate ions, and Na plus ion. Now let's take a look at all of the stuff or all of the features that we can see in this acidic buffer. So number one, you can clearly see lots of ethanoate ions, right? Every single sodium ethanoate molecule has dissociated into ethanoate. And plus you also have some ethanoate ions because of the dissociation of the weak acid. So you see lots of ethanoate ions present in the buffer solution. You also see lots of mainly unionized ethanoic acid molecules. Now, some students ask me this, why is this unionized? As in, why do we write mainly unionized or majority of ethanoic acid molecules are unionized? It's because, let me get the spelling right first, unionized. Yeah. It's because, remember, partial dissociation takes place. Now, some students think that when we say the word partial dissociation, they are like, okay, if we have 100 ethanoic acid molecules, 50 of them dissociate. That's partial dissociation. No. Partial dissociation means if you have 100 molecules, out of this, there is going to be negligible dissociation, meaning one or maybe even two, if you're lucky, dissociate. How many are left which are undissociated? 98 molecules are undissociated. So before everything happened, you had 100 ethanoic acid molecules, and at the end, you have 98 molecules. Is this change negligible? Of course, it is negligible, right? You start with 100 and you end at 98. It's the same thing as starting with 100 ml of water in a glass and ending with 98 ml. It doesn't make difference. It doesn't make any difference. It's almost the same thing. So we say that the change in the ethanoic acid molecules, why did this change happen? Because remember, some of them dissociated. So this change in the ethanoic acid molecules is negligible. So you have lots of mainly unionized ethanoic acid molecules present. And remember, we said that the change is negligible, meaning that if, let's say in the questions that we do later, if the question is asking you to find out the final concentration of CH3COOH, you don't need to worry about it because remember, it's the same thing as the initial concentration of ethanoic acid way before you started making the buffer solution because only one or two of these dissociate. Okay, now if one or two dissociated, doesn't that mean that there are only going to be one or two protons present or one or two hydrogen ions present? Because look at this, the only way that protons are formed in the solution is because of the dissociation of the acid. So there's only one or two in the solution. Now, is this way too much? Of course not. It's just one or two. But the thing is, one or two hydrogen ions are enough to make the solution acidic. So you have negligible, or I wouldn't say negligible because negligible means you aren't taking it into account. We are taking it into account. We are saying there are very less H plus ions. However, they are enough to make the solution acidic, right? Any solution becomes acidic because it has protons in it. And any solution becomes basic because it has hydroxide ions or OH minus ions. So, but it is enough to make the solution acidic. Okay, now there's one more thing you need to know about. And this is expanding on point one. If I ask you to write down an equation for calculating the total ethanoate ions present in the solution, how would you write it down? You would say that if I have to calculate the total ethanoate ions, I would write down the concentration of sodium ethanoate, and we'll understand this why are we writing this in a second. Concentration of sodium ethanoate plus the concentration of ethanoate ions produced from the dissociation of the acid. Now, I know this equation doesn't make sense. Let's understand this. What are the two things which are adding up to give you the total ethanoate ions in the solution? Number one, concentration of sodium ethanoate. Take a look at the chemical equation. It's saying that 1 mole of sodium ethanoate completely dissociates to form 1 mole of ethanoate ions and 1 mole of sodium ions. Why am I saying 1 mole? Because look at their coefficients. Now, remember, if and write this somewhere in your notes, if the reaction is not reversible, meaning if the reaction is reversible, uh, sorry, if the reaction is irreversible, meaning it only has a forward reaction, there's no sort of backward reaction. In that case, you can use stoichiometric ratio. Let me write this. If a reaction is irreversible, you can use stoichiometric ratio. I hope you guys know what stoichiometric ratio is. That if 1 mole is formed here, then you look at the ratio here of their coefficients. This is 1 and this is 1. So whatever the number of moles of sodium ethanoate were, that's the same number of moles of ethanoate ions. Why? Because their ratios are the same. If let's say this was 2, then whatever the number of moles here were of sodium ethanoate, let's say X, in this case, the moles of ethanoate ions would be 2X. If this was 1 and 3, and if this was X moles, this would be 3X moles. So it's just the ratio. So if the ratio of the coefficients is 1 is to 1, if this is X, this is also X. So if I have to calculate ethanoate ions, can't I just calculate sodium ethanoate? And it's basically the same answer, right? So concentration of sodium ethanoate plus concentration of ethanoate ions which are produced because of the acid dissociating. Take a look at this again. There are two ways in this acidic buffer in which you are producing ethanoate ions by the partial dissociation of the acid and the complete dissociation of the salt. Now, we took this into account, right? We wrote that here. But if you take a look at this, we said that the change in the acid concentration is negligible, meaning 1 or 2 acid molecules dissociate. So, if 1 or 2 molecules dissociate, 1 or 2 molecules of ethanoate ions, these ones are gonna be formed. So, how many are you forming here? 1 or 2. 1 or 2 is negligible. So, we say that this entire thing in the bracket, this is negligible. So, what was the purpose of me trying to explain this whole thing? This is what you need to understand. If in a question or in a formula, it asks you to calculate the total ethanoate ions, you will say that this is equal to the concentration of sodium ethanoate. That is it. Now I'm using the example of sodium ethanoate and ethanoic acid. Any other example, just change up the name of the formula and that's it. So this entire thing is negligible, meaning these ethanoate ions produced by the acid, we are not taking them into account just for our simplicity of the equation, just for making the equation more simple. We're saying, we're assuming that all of the ethanoate ions in this entire solution, in this entire beaker, come from the dissociation of the sodium ethanoate. That's it. Now I have a few questions for you to solve. So just pause the video after I've done writing the question and solve it, and then resume the video once again. So write the expression for Ka for this acidic buffer. I'm gonna give you guys an acidic buffer, and you have to tell me what the Ka equation is gonna look like. So the acidic buffer which I have is ethanoic acid partially dissociates into ethanoate ions and H plus ions, and then I have sodium ethanoate which fully dissociates into ethanoate ions and sodium ions. So try to write down the Ka expression for this. Okay, I'm going to assume that you guys have solved it by now. So let's see. Ka stands for acid dissociation constant. in this chapter, you might have learned of many equilibrium constants, right? So in AS, you learned of Kc and then Kp, and now in A2, you started with Kw, then Ka, then Ksp, then Kpc, and there's one more I forgot. So all of these equilibrium constants. Ka is acid dissociation constant. It's an equilibrium constant which you use only and only if you are dealing with weak acids. Is this a weak acid? Yes. So we can use Ka in this case. If it's not a weak acid, let's say it's HCl or H2SO4, which completely disassociates, you cannot use Ka. It's not allowed. So how do you write the expression for Ka? A trick to remember this is you write it in the same way in which you write the formula for Kc. So how do you write the formula for Kc? It's concentration of products divided by the concentration of the reactants. Same case here. So Ka, write the concentration of the products first. So the first bracket is going to be CH3 COO minus. Also, please just use square brackets because remember, square brackets are actually mole per decimeter cube. They are code word for mole per decimeter cube. If you use these brackets, the examiner is going to mark it wrong in the exam. You have to use square brackets. So CH3COO minus and then H plus. That's the two products. Their concentrations are multiplied, divided by the concentration of the reactant CH3COOH. Now, if some students are confused on why didn't I make the Ka equation looking at this and why did I make it only looking at this? It's because Ka is used for weak acids. Is this a weak acid? No. This is a weak acid. So I make it based on this equation. So CH3COO minus times the concentration of the proton divided by the concentration of the acid. Simple as that. So the question I have is, what is the pH of a buffer solution? Obviously, it's talking about an acidic buffer because I haven't taught you guys basic buffer. So what's the pH of a buffer solution which is made by making up 1 cubic decimeter of solution containing 1 mole of ethanoic acid, so CH3COOH, and 1 mole of sodium ethanoate, so CH3COO. And I've used the same compounds or the same species as in the example, so it makes it a bit easier for you. And the Ka for ethanoic acid, obviously, because that's the weak acid in this question, is 1.74 times 10 power minus 5 mole per decimeter cube. So try this out. Okay, I've assumed you've solved it now. So how are we going to solve this? Look at what the question is asking for. The question is asking you for the pH. And how do we calculate the pH? Using a simple formula. And that is pH is equal to minus log base 10 concentration of H plus ions. This is the formula which you need to remember. This is the basics of this chapter. So pH equals minus log base 10 concentration of protons or concentration of H plus ions. It's asking you the pH of a buffer solution which is made by making up 1 cubic decimeter of solution. So basically it's telling you that the total volume of the entire container, the entire solution is 1 dm3. And it contains 1 mole of ethanoic acid and 1 mole of sodium ethanoate. Highlight the two compounds that are given to you in the question. Now, step 1. You know that it's an acidic buffer, right? How do you know it? Because it's using a weak acid and the salt of the weak acid. It's making a mixture out of it. So, make the buffer solution to make life easier. How do you make the buffer solution? Write the two equations. CH3 COOH partially dissociates or fully dissociates? partially dissociates into CH3 COO minus plus H plus, and then CH3 COONA fully dissociates to form CH3 COO minus plus Na plus. That's the acidic buffer which we have got right here. Now, it's given you the Ka. It has given you the Ka value. So, write the equation for Ka using the equation for the weak acid. So this is going to be CH3COO minus multiplied by H plus divided by the concentration of the acid, which is CH3COOH. Now, to find pH, you need the concentration of H plus ions, meaning you need this value right here. Now, you have this, you need to find this and this to get this, right? Then it becomes a simple algebra equation with one unknown variable. So the goal right now, first get your goal right. Your goal right now is we need to find the concentration. I'm gonna write that in square bracket of ethanoate ions, CH3COO minus ions, and goal number two is find the concentration of the ethanoic acid. This is their equilibrium concentrations. Why? Because we are finding their concentrations when they are part of an equilibrium constant. So you don't need to find their initial concentrations. You need to find their final concentrations, their equilibrium concentrations. So be careful of that. Okay. Goal number one, finding the concentration of ethanoate ions. Think about it. There's an equation which we made right here. The total ethanoate ions in the solution, we said this was negligible. The ethanoate ions produced from the dissociation of the weak acid, we said this was negligible. So basically, we're saying that all of the ethanoate ions in the solution are basically just equal to the concentration of the sodium ethanoate. Why? Because we can apply a stoichiometric ratio here of 1:1 ratio. So, what is the concentration of sodium ethanoate? They haven't given us the concentration, they have just given us the moles. But you've learned a formula in IGCSEs and AS levels, C equals N over V. When you have the moles and the volume, you can find the concentration. So 1 mole divided by 1 decimeter cube being your total volume is equal to 1 mole per cubic decimeter. Always remember, the volume which you write right here, this is the total volume of the container. It's not the volume of the acid, right? Because you try to find out the concentration of the whatever in the container. In different containers, the same sodium ethanoate will have a different concentration. So let's say if I take 10 ml of sodium ethanoate and I take a container, I take a beaker, I put 10 ml of sodium ethanoate. And now I put 100 ml of water inside of it. The concentration is going to decrease because I'm diluting the salt. I'm adding water to it. Let's take another example. I take another container, I add the same 10 ml of a sodium ethanoate. But this time, I add only 2 ml of water. The concentration is going to be higher. It's going to be different because I have added less water here. I haven't really diluted the salt too much. So always remember, whenever you find out the concentration of any compound, the volume you use needs to be the total volume of the container. So the total volume of the container was 1 dm cube, which is why we used 1 here. The unit for this is decimeter cube, and the unit for this is mole, which is why this becomes mole per decimeter cube. So you have the concentration of sodium ethanoate. And remember, the salt's concentration is the same as the anion's concentration, which is the ethanoate ions. So goal number one is accomplished. This value is 1 mole per dm cubed. Goal number two, find the final or equilibrium concentration of the acid. Remember what we talked about, that the initial concentration of the acid equals the final concentration. Why? You guessed it right. There is negligible change in the concentration. So, what's the initial concentration? Again, 1 divided by 1. That's equal to the final concentration. So, if you have to find out the concentration of the acid, that's just C equals N over V, which is going to be 1 divided by 1, and that is just 1 mole per decimeter cubed. Goal number 2 also completed. It's a very simple equation now that this is 1.74 times 10 power minus 5. Take the concentration of the acid to the other side, multiply this by 1. Take the ethanoate ion concentration to the other side. This becomes the denominator, which is also 1. And this is the concentration of the proton. So that's, oh, why am I using a calculator? This is multiplied by 1 divided by 1. It's just this. So now, final step, pH equals minus log, put the base as 10 of the logarithm, and then 1.74 times 10 power minus 5. So now I need a calculator. Minus log 1.74 times 10 power minus 5. This comes out to be 4.759. And always remember, pH is to two decimal places. So this becomes 4.76 as the pH. What is this sign right here? This is called the approximation sign. There is a sign for equals to, right? This and this. For approximation, when you have to show to the examiner that this is approximately equal to this, you use a wiggly equals to sign. Now, let's take another question. Now, I'm just increasing the difficulty up a notch. So let's see. You have a buffer solution, again, acidic buffer, and a buffer solution was made by mixing 50 cubic centimeters of zero point 0.3 mole per decimeter cube of ethanoic acid. And this is the point when you know that this is an acidic buffer question. With 100 cubic centimeters of zero point 0.6 mole per dm cube sodium ethanoate, so CH3COONA. You need to calculate the buffer solution's pH if the Ka value is equal to 1.74, again the same value of course because you're using the same acid, 1.74 times 10 power minus 5 mole per dm cubed. So let's try this out. Okay, I'm gonna assume you guys have solved this. If not, let's solve it together. So take a look at the question again. What's the question asking from you? It's asking you the pH. That's the main part, right? So you know the formula for pH. There is only one formula in your syllabus. There are also different formulas. For example, pH plus POH equals 14. Absolutely useless. Not in your syllabus. No need to use it. There's only one formula, which is pH is equal to minus log base 10 concentration of H plus ions. So again, same goal, you need the concentration of H plus ions. It's the exact same question as before. You have the Ka as well. First, make the acidic buffer, meaning write the two equations down. CH3COOH becomes CH3COO minus plus H plus, and then CH3COONA becomes CH3COO minus plus Na plus. You'll get fast like this of writing down equations. I'm not flexing. This is just going to be muscle memory if you do multiple questions. So now you need to find out this. Write down the expression of Ka. This is going to be the concentration of CH3COO minus. I'm writing it down based on this equation, multiplied by H plus divided by the concentration of CH3COOH. Now, you have to figure this out. You have this already. You need to find this, and you need to find this. This is going to be a bit interesting because now remember, in the earlier question, the total volume was 1. So if the total volume is 1, you guys must have also heard of this before, that if the total volume of a solution is 1 decimeter cube, moles are equal to the concentration. Isn't that exactly what was happening here? 1 mole of sodium ethanoate, 1 mole per decimeter cube, sodium ethanoate or ethanoate ions. 1 mole of ethanoic acid concentration, 1 mole per dm cube. So if, and you could remember this as a rule of thumb, if the volume is 1 dm cubed, number of moles equals to the concentration. Now, if you might ask why is that, take a look at the formula. C equals N over V. If you divide anything by 1, it's gonna be the same value as before. So moles divided by 1, the concentration is just the same value as the moles. That's bad. But now this is not the case because take a look at the total volume of the solution. 50, 100. VT, total volume, equals 50 plus 100. This is 150 centimeter cube. So now moles are no longer equal to the concentration. Goal number 1, we have to find the concentration of the ethanoic acid. Obviously, the initial is going to be equal to the final. And then goal number 2, you have to find the concentration of the ethanoate ions. So let's try to find the concentration of the acid. Let's look at what is the information that they've given us. So it's telling us that you have 50 cubic centimeter of 0.3 mole per dm cube of acid. Look at the earlier question. It gave you the moles as it is. And all you had to do was divide it by the total volume, and you get the concentration in the buffer solution because C equals N over V. But the thing is, they haven't given you the moles in this case. So it's just an extra step. You have to find the moles from the given concentration. This is important. You have a concentration which is given to you. You convert that into moles. And then you convert that again to the concentration. Now, some of you might ask, if we are just converting concentration to concentration, why don't we just use what is given to us? It's because what you are given is the number of moles in 1 decimeter cube, right? That's what mole per dm cube means. Mole per dm cube means that in 1 dm cube, how many moles are there? So 0.3 mole per dm cube means that in 1 dm cube, you have 0.3 mole. Do we have a solution of 1 dm cube here? No. We have a solution of 150 cm cube here. So you need to convert the given concentration to moles and then moles to concentration. If, and I say if, the total volume was 1000 cm cube, meaning 1 dm cube, then this would be your final answer. Simple as that. But because it's not, you have to first convert it into moles. So what's the formula? N equals CV over 1000. You divide it by 1000 if your volume is in centimeters cube. If your volume is in decimeters cube, then you just write N equals CV because it's in centimeters cube, right? So we need CV over 1000. So 0.3 multiplied by 50 over 1000. What are we now calculating? We are now calculating how many moles, what is the amount of acid that we're adding, because we don't have the amount of acid. Moles definition is, and you must have learned this in physics, it's the amount of substance. So when you're calculating the moles, you're calculating actually how much of a quantity of acid you're adding. So 0.3 times 50 over 1000. You're adding 0.015 moles of acid into the container. Now convert this into concentration. So this is going to be 0.015 mole over 150. Oh, sorry. Convert this to decimeter, 0.15. If you're thinking what's the difference between the earlier question and this question, in the earlier question, you were already given this. In this new question, you're first finding the moles and then the concentration in the container and not the initial concentration. So 0.015 divided by 0.15 is zero point 0.1 mole per dm cube. Now, how do you find the concentration of the ethanoate ions? Again, same case here. Zero point 0.6 multiplied by 100, this and this. So, because n equals CV over 1000, so 0.6 times 100 divide by 1000. So, this basically becomes 60. And then when you divide this by 1000, this becomes 0.06 mole. Yeah, that's it, mole. Now you divide this by the total volume in the container, which is 0.15. So now you have the final concentration, the equilibrium one, which is mole per dm cube. This is done. This is done. So 1.74 times 10 power minus 5, the K, I'm just writing down, rewriting this formula, times the concentration of the acid, which is zero point 0.1, divided by the concentration of the ethanoate ions, which is zero point 0.4, equals the concentration of the proton. So 1.74 times 10 power minus 5. I know my calculator is a bad color. I don't care. Divide by zero point 0.4. This is 4.35 times 10 power minus 6 mole per decimeter cube. So, last step, write the concentration of the proton in the pH formula. So, 4.35 times 10 power minus 6. And the pH, let's see what this becomes equal to. This is equal to 5.36.